let's put this formula into the action actually. Okay, let's put this formula into the action, and let's compute, for example, first volume. Now we all know about the sphere actually. Okay, that if you take a sphere, okay, say of radius r, its volume is 4 upon 3 pi r cube actually. Okay, so this is what the volume of this sphere is. But is it a God-given formula? Indeed, it's a God-given, but we can, make sense of this formula using the intellect. So what we can do? How are we going to start? So I would like to prove actually that the volume of a sphere of the radius r is really is 4 upon 3 pi r cube actually. Okay, so 4 upon 3 pi r cube. So how to do it? Take the sphere, okay, and through its center, okay, say xy axis passes actually. So okay, so xy axis passes through the center of it actually. Okay, xy axis passes through the center of it. Okay. Now what to do? So I know that this area from the origin, which is the middle of the sphere, to this is radius r, and this is also radius r actually. Okay. Now, if I, for example, take a knife, okay, so take a knife. So take a ball, take a knife, and say slice it. Okay, slice it through x-axis. Okay, so it's like cut it vertically. So when you're gonna cut it vertically, so in other words, take for example, an apple or something that is spherical, and say cut it, vertically. So when you're gonna cut it vertically, what picture you're gonna see here? I'm pretty much sure that you guessed it correctly, that you're gonna get a disc. So you're gonna get a disc actually. So if I, take a knife and say cut it vertically, I'm gonna get a disc. I'm gonna get a disc actually that would look like this. Okay, that would look like this. So let me make this disc here as well. Okay, so this is what is the top view. So this is side view, and this is the top view of it actually. Now, what are the essentials of this disc? Okay, so what are the essentials of this disc actually? By the way, if this point is say xy, it has coordinates xy, what would be this distance? This distance is going to be r, for sure. Okay, I know that this distance is going to be r. So it's like the distance between the middle of the sphere to its surface. So this is radius r. Okay. Now, if the coordinates of this point on the surface is xy, what does it tell you about say this distance and this distance? Okay. So if this point has coordinate xy, this means that this distance is x and this distance is what? Okay, this distance is y actually. So you have this triangle, okay, whose one side is r, other is x, and other is y. Okay. Okay, this is what it is. And I want to know that what is the area of this radius? What is the formula for the area of the radius in the terms of x actually? Okay, in the terms of x. Now I know that the area of the disk, okay, is going to be what? By the way, what is the radius of this disk? Keep in view that the radius of this disk is not r, it's this height. And what is this height? It is y. So the y is the radius of the disk. So if y is the radius of the disk, then what would be the area of the disk? It is going to be pi pi y square. Okay, it's going to be pi y square. Now if you want to make area, this area as the function of x, what you need to do, you need to find the relationship between y and x. And how you can find the relationship between y and x? By considering this triangle, okay? By considering this triangle actually, which is ryx. So by Pythagorean theorem, r square is going to be y square plus x square actually, perpendicular square plus base square. That means the area as a function of x is going to be pi multiplied by r square minus x square. Okay, r square minus x square. And once you have once you have the formula for the cross section, then the volume, okay, then the volume of this object can be computed as what? It can be computed as, you know, this formula. So the V is equal to what do you call integrating from A to B. Now what is A to B? Okay, so the A is really from where, you know, sphere starts, and B is like from where sphere ends actually. So sphere starts from where? So this distance is what? So this distance is r. So that means that this point has coordinates what? So it's minus r0. While this point has coordinates what? This point, this has coordinates r0. So what you're going to say? The x-axis, okay, the interval on which the sphere is defined on x-axis is from minus r to plus r. And then I'm saying take the area of x and multiply it with dx. By the way, you can also interpret this dx. So this dx is like, you know, so you have this disk. So this dx is like really, so you can treat this dx as the height of the disk actually, okay, as the height of the disk. So this is one disk, okay, it has a really tiny height actually, it has a tiny width, okay, and that width is, you know, really dx. So the area multiplied by this width is going to be what do you call the volume, and you can compute this volume actually. So the V is going to be something from negative r to r, and A of x is pi times r square minus x square dx, and then you can compute it. You're going to get pi r square, there is no x here, so you're going to get x minus pi r square x minus, you're going to get pi x cube upon 3, and then you need to substitute negative r to r. This is what that you have. So I multiplied by pi r square, and then, you know, computed this. So you're going to get pi r square x minus pi x cube upon 3. So when you're going to substitute, for example, the first value, you're going to get pi r square multiplied by r cube minus, when you're going to substitute the r here, so you're going to get pi r cube upon 3. Okay, this is what that you're going to get, minus, if you take, for example, negative r and substitute it here, so you're going to get minus pi r cube, okay, because minus r multiplied by r square is going to give you minus pi r cube, and minus, if you're going to substitute minus r here, so you're going to get minus pi r cube multiplied by minus, so it's going to be plus pi r cube upon 3. Okay, this is what that you're going to get, and once you compute this, what would be the net result? So this is going to be pi r cube plus pi r cube, so it's going to be 2 pi r cube minus, this is going to be plus minus minus, okay, this is going to be 2 pi r cube upon 3. Okay, and once you compute this number, so it's going to be 3 times 2, 6 minus 2, so you get 4 upon 3 pi r cube, which is the volume of this entire disk. okay, which is the volume of this entire sphere. So I hope it's making a little bit of sense to you. It's not difficult, you know, you can. So the key thing is that, okay, take your object, put it in XY axis, and then along X axis slice it, okay, slice it, and see what is the cross section. Try to find the area of that cross section, and then integrate that area of the cross section, you know, over the domain of X, whatever the domain of X is. So we sliced it. So when we sliced it, we got a disk of the radius y. So its area become pi y square. So I need it in the terms of the function x. So I deduced actually this triangle. So hence you get a of x to be pi r square minus x square. So I got the area in the terms of x. And then this entire sphere is defined on the interval minus r to r. So therefore I integrated from minus r to r. Okay. Therefore I integrated from minus r to r actually. Let's do some more examples, and you can based on the same point. So the next is an interesting example. So it says take a curve y equal to square root of x. Okay, take a curve y equal to square root of x. Okay, treat this curve as like something solid. So treat it as like a curved stick actually. Okay, so it's a curved stick. Okay. Then it says, take this stick and rotate it around x-axis. Okay, so rotate it around x-axis. So when you're going to take this stick and rotate it around x-axis, okay, it is going to create, you know, what do you call a volume actually. Okay, so when I take, for example, this curve and I rotate it around, you know, some axis, then you know it makes a shape actually. So it's going to make a shape actually. Okay, you can also treat it as like, okay, take this stick, but this stick is like magical stick that when you rotate it, it leaves its impact. So when you're going to see the impact, the picture that you know you get by rotating this curved stick, you're going to get a shape actually. Okay, we call it solid of revolution. Okay, and the question is, what is the volume of this picture? So the first thing, so in other words, rotate, take y equal to x on interval 0 to 1. Okay, so it starts from 0 and say ends at 1, and then rotate it. So when you're going to rotate it, what are you going to get? Okay, you're going to get, you know, a picture like this. Okay, you're going to get a picture like this. So it's going to sweep out, for example, a picture like this. It's going to sweep out a picture like this, something like this. Like it should be balanced on, like it should be symmetric actually. Okay. So if I say it could be something like this. Okay. I need to work on my drawing skills. Alright. So I took this curve and rotated it. When I rotated it, I get this bowl-like shape actually. And the question is, what is the volume of this bowl? Okay? What is the volume of this bowl? So what will be our strategy? Okay, so this is really the interval 0 to 1. This is 0 to 1. So this is 0, not x, but 0 to 1. So what we're going to do? We're going to do the same. Take, say for example, a knife. You have to imagine a lot. Okay? Take a knife and slice it. So when you're going to slice it, it is going to create a cross section here, and that cross section is for sure going to be circular. Okay, this cross section is going to be like a disc. Okay, so for example, this picture is not like that, but imagine this looks like a bowl actually. So if I, for example, slice it from here and see the top view of it, the view of the top is going to be look like a disc actually. Okay, it's going to look like a disc. So when you slice this bowl at a random point, it's going to look like a disc. And for example, if the coordinates of this point are x, y, okay, the coordinates of this point are really, what do you call, x, y. The question is, what is the area of this disc? So let's make it like that. Let's make it like that. What would be the area of this disc? In order to know the area of this disc, I need to know the radius of this disc actually. And what is the radius of this disc? The radius of this, so if this point is xy axis, that has coordinate xy coordinates, that means that this distance is x and this height is y actually. Therefore, this point is going to have coordinates xy. So this distance is x and this height is y. Okay? So in other words, the radius of the disk is really y. Okay? Is really y. So what would be the area of this disk? The area of this disk is going to be pi r square. But the radius is y, so it's going to be pi y square. But y is the square root of x. So it's going to be pi square root of x squared, so it's going to be pi x. So hence you got, the area of a cross section of this bowl. And once you have it, then you need to do what? In order to compute the volume. Okay? Just integrate. So take this a of x, integrate it with respect to dx. From where to where? From the point from where picture starts and from the point where picture ends actually. So the picture starts from x equal to 0 and it ends at x equal to 1. So you need to integrate it from 0 to 1. Okay? You need to integrate from 0 to 1. So if you substitute the value 0 to 1, you're going to get pi x dx, and if you compute it, you're going to get pi x square over 2, and then if you substitute 0 to 1, you're going to get pi by 2. So this is really the volume of the curve that you get by rotating the curve y equal to square root of x around x-axis, okay, around x-axis. How about if I make a rotation around y-axis? In other words, for example, I have this curve. Okay, for example, I have this curve. So it says find the volume of solid obtained by rotating y equal to x cube. So what would be y equal to x cube? I know that the graph of x cube looks like this actually. Okay, but I have to consider only the graph of x cube in positive y-axis, okay, in the first quadrant. And so we need to consider, what do you call, y equal to x cube. So I need to consider the region between y equal to x cube and y equal to 8 actually. So where is going to be y equal to 8? So imagine that this is y equal to 8 actually. So this line is y equal to 8. Okay? And what we have to do, so treat it as like a stick actually, okay? Treat it as like a stick and rotate this stick around y-axis. Okay? Rotate this stick around y-axis. So when you're going to do it, what you're going to get? Okay? When you're going to do it, what you're going to get? So you're going to get, okay, you're going to get a picture like this. So let me do it through coloring. So I took this, rotated it. So by rotating this cube curve y equal to x cube around, say, x-axis, you're going to get this actually, where you know this top radius, top is y equal to 8, okay? And obviously this below is y equal to 0. Alright. And I want to compute this volume. So how can I compute this volume? So this time I need to slice not horizontally. I can do it, it's not a big deal, I can do it. But the better would be that if you slice it horizontally. Previously you were slicing it, you know, vertically because the rotation was around x-axis. So if you have rotation around the y-axis of a curve, slice it horizontally. So when you're going to slice it horizontal, so for example, you take this point and you put a knife, so you're going to get a slice, but this slice is going to be again a disc actually because this is a bowl shape. So it's going to be a disc. Okay? It is going to be a disc. And what are the coordinates of, for example, this disc? So imagine if I call this point as xy, okay? So this means that this distance is y and this distance is x actually. Okay? This distance is x. In other words, the radius of the disk that you get through the slicing is x in this case. Okay. And if the radius is x, what would be the volume of it actually? So area of it. So the area of it is going to be pi x squared. But I need to, okay, I need to convert this, since this is a curve like between y equal to 0 to y equal to 8, so I need to make this area dependent on y. In other words, my formula is not going to be now depending on x, but it's going to be depending on y. And it starts from 0 to 8 actually. So it's going to be y. So can I express this x square in the terms of y? The answer is yes. I know that y is x cubed. So if y is x cubed, okay, that means y power 1/3. So if you take the cube root, is going to be x. And if this is the case, you're going to get pi y power 1/3 and square. So it's going to be pi y power 2/3. So this is really the area of the disk in the terms of the y. So if you want to compute the volume, okay, if you want to compute the volume of this bowl, so what you need to do, you need to integrate the area as a function of y with respect to dy, okay, and from where to where, so that it starts from 0 and it goes up to 8. You know, I mean, if you wish, you can really, interpret this dy as well. So for example, you have this one slice, okay, so you took this point x and you did the one slice. So for example, you take another point really close to this point and consider another slice actually. Okay, consider another slice. So when you're going to consider another slice, okay, you're going to get what? You're going to get this ring actually, okay? You're going to get this ring. Okay? So the width of this Okay, the width of it, this width, this is really dy. Okay, this is really dy or delta y. Okay, and the area of it is a of y. So a of y multiplied by say width or height, whatever you call it, so it's going to give you the volume, and then you're summing up all these volumes from 0 to 8. Anyway, but you know, this description is unnecessary. You just need to compute a of y or a of x and then simply integrate. So when you're going to integrate this from 0 to 8 and pi y power 2 over 3, so I'm directly writing it actually. Okay, so you're going to get 96 pi divided by 5. Okay, and you get the volume of this solid of revolution. Okay, solid of revolution. Why I'm calling it solid of revolution? It's like take a curve, okay, take a curve and rotate it. So take a curve and rotate it. So you're going to take a curve and rotate it. It is going to span a volume actually. Okay, it is going to create a volume, and that volume is going to be the volume that is a result of a revolution. Okay, and therefore you call it a solid of revolution. So I hope you got, you know, some sense of it. There are other methods as well, like washer method and disk method and, you know, shell method. I'm not going to get into that. I'm just giving you some glimpse of it that you can get into the volume. You can compute the volumes of the solid of revolution. We will talk about the other methods kind of in a more concrete manner in our Calculus 2 course, or in our next course actually. Okay, so you see what do you call the outcome of all this stuff, that, you know, by this amazing formula, in other words, by the means of integral, you can really compute also volumes actually. Okay, not only areas but also volumes. So this is something very interesting. Let's move towards another interesting application of integrals. But before moving towards another application of integrals, let me recall what you call the parametric curves. Okay? What do you mean by parametric curves actually? And using parametric curves, we will do a very interesting thing. So what's a parametric curve? So imagine this is time axis and this is xy plane. Okay? This is time axis and this is xy plane. Imagine that at each time instant, so it's like a clock that is ticking actually, okay? It's ticking continuously, So you have a clock, okay? You have this time that is moving forward, okay? Going forward actually. At least it gives an illusion, okay? Because the modern physics says something very, you know, strange actually, that probably we don't understand even time. Okay, so it's like moving ahead in future, okay, is an illusion actually. Anyway, so just treat this as like time axis in which each point is like an instant, okay? Each point is like an instant actually. Now to each instant here, I'm associating a position. So imagine you have a particle, okay? And you are saying that at this time instant particle was here, at next time instant particle was here, at next time instant particle was here, at next time instant particle was here. So if you combine the all positions of the particle, you're gonna get a curve. You know, what you're gonna get? You're gonna get a curve in xy axis actually. Okay? So if I take, for example, an arbitrary time, let's call it t, say at this instant when the clock was showing this time, the particle was here actually. It was at some location here. And let's say the coordinates of this point, okay? So the coordinates of this point, so in other words, at time t, the particle was at location xy, okay? It was at the location xy. But I want to keep track of this time actually. So I want to say